All right, the time is now 9:31. I'm sure as we get some of these housekeeping notes underway that we'll start to have a few more people joining us. So we will go ahead and get started here on this presentation. Good morning and welcome to our virtual Skywarn course. Thanks so much for joining us this morning. We should have a few more attendees on this morning, but a few housekeeping notes before we get started. If you look at your GoToWebinar panel that opens up there on the side, there is a panel for questions, and I will be monitoring that from time to time, and we'll occasionally have breaks in the presentation to review some of those questions. And then I also have a number of polls for some review questions as we go throughout. Don't worry, none of these are graded, but just to help make sure that the concepts are being understood, we'll have some of those review questions as we go on. And if you have a specific number about a certain slide, each slide is numbered, so we can use that to help us go back and refer to any of those slides. So with that, let's begin our NWS Burlington Skywarn course for winter season hazards. So what we'll discuss this morning is what Skywarn is and what does it mean for us here at the National Weather Service. Skywarn plays a critical role, and we'll discuss why that's so important for us to have trained spotters. We'll give an overview of who we are and what we do here at the National Weather Service. Talk a little bit about winter hazards and safety, the different kinds of winter weather we can experience and common winter storms, that storm tracks, climatological features, things like that we can observe. And then of course, how to measure snow and ice and the best way to accurately report that data to us. We'll also go over reporting methods like MPing, which is an app you can download on your smart devices and provide real-time spotter information in that method as well. And that stuff is also going for national research as well. So what is Skywarn? Skywarn is a national network of volunteer observers that are trained by the National Weather Service. So basically started all the way from amateur radio back in the late 60s, early 70s. The idea being if communication failed, that secondary measures through amateur radio, using those you can relay reports and keep that line of communication open when mainline communication fails. Reporting any kind of significant weather. Typically, most spotters report severe weather, things like tornadoes. Since we don't get as much of that up here, most of our observers provide information to us about snowfall accumulations. So who can be a weather spotter? It did have its origins in amateur radio, and then it kind of branched out to some of the surrounding groups like emergency management and local officials. But over time, it's continued to grow to include researchers, academia, members of the media, and of course, the general public. So in other words, anyone can be a spotter. So what kind of information do we ask our spotters to provide? The primary purpose is for severe weather, like reporting funnel clouds, tornadoes, wind damage, especially since we have a lot of trees up here and a lot of areas that might not be super populated. Wind damage is often one of those key things, as well as hail, flooding, which can include ice jams, of course. And then for us, oftentimes our spotters provide information about heavy snowfall. Of course, it can be anything though. We have a number of spotters who, whenever it rains, they start their day by giving us a phone call of the rain that they received that day. So if, as a weather spotter, all you would like to report is information like rain amounts and snow, that's entirely up to you. The level of involvement is, it's a voluntary program, so how much you want to participate is entirely up to you. We do appreciate any information that you pass along, but none of it is obligatory. It's not like you have to regularly or routinely provide information. It's all based on what you're able to do. So how do they report the information? A spotter is as specific as possible. Things like who, what, when, and where are all very important features for our spotter reports. Since we might not always be as familiar with your local towns or your roads, it's important to reference nearby intersections, landmark features, and things like that, so we can pinpoint that information to radar imagery or to provide the most accurate mapping when we provide those maps. And of course, let us know who you are. We are not always, we're rotating shift workers, so it's different people working, so we're not always aware of our spotters and their reports as they come in. And sometimes it's important to know how long certain weather phenomena lasts, like hail. Is the hail very brief or short, or did the hail last a long time? Or with the idea of transitioning precipitation types, how long did we go from freezing rain to sleet to rain? Some of that can be really important information for us. So why is it that we need spotters? We have all kinds of technology, automated weather stations, satellite data, radar, computer models, all of these different resources that we have to view and observe the weather. But ultimately, all of these technologies have their own limitations. Each of them have something that they can't quite see or might not be able to resolve perfectly, and a spotter comes in and provides that critical ground truth information. So here's an example of a radar's limitation. Radar takes a scan across the atmosphere, and I thought I had removed the sound from that, but I guess it's still there. So radar is doing scans across different elevations of the atmosphere, and it might undershoot a storm that's close by. Sometimes we'll call that the radar's cone of silence, where it's unable to see from a certain viewing point no matter what angle the radar is viewing from. Or a radar might be seeing a storm that's quite far away, and as a result of the distance from the radar, it's seeing stuff that's very high up in the atmosphere, as opposed to what's exactly happening at the ground, which is very relevant for tornadoes especially. And if you live in any part of eastern Vermont, or you live west of the Adirondacks in New York, you are well aware of the mountain beam blocking that happens in our region, where it's really hard to get a picture of what's exactly happening in eastern Vermont. If there's any kind of shower that sits below 4,000 feet, the radar essentially cannot see any of that rain or snow that's happening in eastern Vermont. But of course, radar does look at varying tilts of the atmosphere. So as you do go up, especially if the storms, if it's a thunderstorm especially, it'll have more vertical depth. And so it can usually start to detect those as you go up the radar scans. But anything that's low to the ground, our mountains block the radar beam and prevent us from seeing what it is over there. So oftentimes we will get reports from spotters that say, hey, there's snow in our area, and we have to take their word for it because radar simply can't see it. So a radar might see the top of a thunderstorm, but a spotter might be able to see wall clouds or those pesky snow showers that radar might not be able to detect. And the reports that you send can help adjust our forecasting and our messaging and our warning services. So in that case, it can be critical and potentially life-saving, the information that a spotter can provide. So bringing this into the scope of winter, in March of 2020, we had a period of brief heavy snowfall rates. We were anticipating the potential for the heavy snow. We knew there was the idea that there could be 1 inch per hour snowfall rates, but we received a report from one of our spotters in Addison County, and they reported that they got 6 inches in a matter of 2 hours. And so based on their call, we were able to update our forecast messaging. We essentially had to double the amount of snowfall expected in parts of central Vermont based on how heavy the snowfall report was. So their phone call to us was critical to us adjusting how the forecast message went. So with all that, we've covered the idea of who can be a spotter, what they report, and why we need it. If becoming a spotter is something that you're interested in, as a reminder, it's completely voluntary. So there is no kind of membership fee. It's all completely free. We just ask that you are trained by a forecaster from the National Weather Service through something like this virtual course here. Of course, it's important to have these reminders as well for those who are already part of our program, as well as through an in-person spotter talk or presentation. It's been a while since we've gone out, but if you have a community need and have a large enough group, we're happy to go out and do in-person presentations again. And then, of course, we have the Comet MetEd course that you can take, and that is a self-paced learning course. Each one is about 2.5 hours, so you can complete it in one good sit down. And that course as well, we get notifications if people complete those in our area. So upon completion, we do ask for the physical address of where you are, and we may do cold calls in the case that we do see severe weather in your area and are looking for a little bit of that ground truth information. So that's part of why we ask for your physical location. Another reason is because every National Weather Service office operates their own spotter network. So in the instance that you are not in our forecast area, we might pass you along to your local National Weather Service in your area. So with that, where is it that we service? We here at the National Weather Service in Burlington forecast for the areas of pretty much most of Vermont and the 4 northernmost counties of New York. So note we actually do not have Bennington or Windham counties. Those sit under the responsibility of the National Weather Service in Albany. So what is it that we do here from a day-to-day kind of service? What does our operation look like? We have at minimum 2 people here every day working 24/7 all day, centered around the clock, every calendar day of the year. The weather doesn't stop, so neither do we. We have routine duties like issuing our various forecasts, providing warning services, and things like that. We have we provide the weather and climate observations for our local area. We send out the daily high, low, how much rain was received, and of course, when we get to that point, how much snow is received. So we quality check all of that information running in for our local area and then send that data out. We also produce, of course, the weather forecast information that will go to either public service or messaging with our partners. We do community outreach, such as these virtual courses. And of course, we also have tours. We are based in the airport, and with the COVID era, we prefer having planned tours, but you're welcome to, if you are in the area or have a small group, to come in and tour our facilities to get a better sense of what we do here. We also do awareness campaigns. We recently did our weekly winter weather awareness week, which was the first week of November, and of course our spotter training. We work with local emergency managers and partners, city officials, road department of transportations, and things like that. We'll be doing some calls later today surrounding the upcoming winter weather event that we have here. And then we also work with our Forest Services, FAA, the USGS, especially with our rivers, and of course our media and academia. So all of these, just beyond weather forecasting, we do a lot of outreach as well to ensure that what we're communicating is effective. We want to make sure that our message is understood and that the forecasts that we provide are at least well understood and well communicated. So with that, we are just a small part of the National Weather Service because it is a national weather service. But each region is broken up according to some of the common geologic features. With the headquarters, we are under Eastern Region, and the headquarters for that is located on Long Island, New York. And of course, there are Western Region offices for the areas like the Rockies, the Central Region that covers many of the plains, and the Southern regions that cover areas usually affected by the Gulf of Mexico. And then from those regional centers, you have the national centers like the Space Prediction Center and Boulder. You have the Storm Prediction Center, fittingly in Norman, Oklahoma, that focuses on thunderstorm forecasting. There's the Climate Prediction Center as well. And then each of the different river forecast centers, which focuses on a lot of the basins, basically how water flows across those areas as rainfall falls. Where will the water go once it reaches the ground? And then, of course, there are all of the offices. There are 122 offices across the United States, 2 of which are even in the Pacific Islands where we still have bases, like American Samoa at Pago Pago and in Guam as well. So we have Weather Service offices all across the nation to provide these kind of forecast services, to provide warning information, and manage the outreach for our local communities. All right, so we are at the first of our review questions here. So I'm going to launch this poll here real quick. So when you report weather, what information should a spotter provide? So there will be multiple correct answers for this. Go through and you should be able to pull that menu off on the tab there from GoToWebinar. All right, it looks like all the answers are in. Let's see, I'll close the poll now. And I believe it should show the, oh, nope, it doesn't quite show the, does it show the results in the tab? Sorry, this is my first time using these polls. Oh, there we go. There's a share button. Okay. So here is what we have for the results. When you report weather, what information should you include? Yes, what, when, and where, what kind of weather phenomena you're seeing. Of course, who you are is very important, and then how long did it last as well. This is all kind of the information that we'd like to see. It's glad to see no one put the vehicle accident. If you see a vehicle accident, it's first thing is call 911 in those situations. And then, of course, the view of Maretail Cirrus, it looks very pretty, but that's not necessarily information that we need. All right. Back over to this monitor. All right. So excellent. That is all of what we need from our weather spotters. At this time, are there any questions out there before we get started on some of the winter hazards and safety? All right, I'm not seeing anything at the moment, so we will go ahead and head into our winter hazards. All right, so here is the first of our, of course, major winter hazards is dealing with slick road conditions when snow or ice causes hazardous road conditions. So this can be a year-round issue that we deal with here. When it comes to injuries due to snow and ice, about 70% are the result of vehicle accidents, and about 25% come from people getting stranded out in storms. So hazardous driving is usually the main impact from our weather here. It's important to keep a winter kit ready in your car with recommended supplies, including blankets and extra coats, the shovels, flares, a bag of sand, tire chains, just in case if you don't have snow tires. And of course, to have plenty of windshield wiper fluid and jumper cables if needed. And then to know the roads before you go, to have multiple ways to receive weather information, to make sure that the weather forecast hasn't changed and impacted your roads. And then, of course, understanding our watches and warnings, our understanding the terminology of the products that we issue is important as well. And then have a dependable source to receive your weather information. So one of our big winter threats is, of course, freezing rain. We actually receive some more freezing rain compared to most other regions in the United States. Especially the Messina, St. Lawrence Valley, looking at the number of average hours annually between 1932 and 2001. So yes, it could probably use a little bit of an update, but across nearly 70 years of data, we typically average anywhere between 15 to 20 hours of freezing rain annually per year. And the time that we see freezing rain most often is in the month of December. So December is the month where conditions are starting to become cold enough at the ground where getting towards the astronomical start of winter, but we still can get warm air aloft that helps produce freezing rain. Whereas at the shoulder of the seasons, we actually tend to not have too much in the way of freezing rain. And then one of our other big winter hazards is ice jam flooding. And this is something that our spotters can also provide as we get into the winter season, is to, if you happen to be driving along different rivers and happen to spot an ice jam, to report that information to us. That has big implications to hydrology, especially when the breakup happens. So there are two different kinds of ice jams that we look for as the season goes on. As we start the season, we look for the possibility of freeze-up ice jams. They typically occur early in the season with that first good cold snap, especially when you have temperatures below 0 degrees Fahrenheit for several days. You start to build some of that frazzle or sheet ice that starts to coalesce, and it happens much more rapidly at temperatures below 0. So when you get that first good cold snap, that can cause freeze-up ice jams. And then the second kind is most often in the spring season, the breakup ice jams, when river rises become greater than the current ice thickness, and that can come from a combination of heavy rainfall, snow melt, anything like that can cause ice jams to occur during the spring season. And typically it happens where rivers start to wind, where water starts to really slow down across the stream. And so that can happen at the confluence of rivers as well, or as you get into lakes as well. I see a note here that one of our participants is in Arkansas. You're welcome to stay on if you would like, and I can pass along your information to your local National Weather Service if you'd like. Understand things, especially like ice jams, might not be as relevant, and we will be going over some of the climatology for information here in Vermont and northern New York. So some of it won't really translate, but you're welcome to stay on if you find the information useful. So that's up to you. But then it's important to know the history of flooding in your area. So be prepared to seek higher ground if you're in a flood-prone region to these ice jam floodings. I have a few photos here of some more of a significant ice jams that have occurred over the years. So it's important to understand your flood climatology and whether or not you face that threat of ice jams if you're in those low-lying areas near some of these slow-moving or winding streams. And of course, another hazard that can come during the winter season is extreme wind chills, especially up here when we get a cold northwest wind. We can get wind chills that reach about 20 to 30 below 0. And in those cases, frostbite can set in as early as 10 to 30 minutes when skin is unexposed. So it's important to bundle up in these extreme wind chill cases. And when we get to 30 below for the wind chill, that's when we start to issue winter weather or wind chill warnings. So we recently hit that here in January of 2022, where we did reach that criteria for a few hours here at the Burlington airport, and a very nice Arctic intrusion that we had. So the reason why wind chill is of a particular concern, when you don't have any wind, the radiational heat off of your own body produces a thin veil of warmth around you that can protect you from some of those cold temperatures. But under windy conditions, that heat is carried off by the wind. So in that case, your body's natural heat doesn't protect you as well from hypothermia or frostbite. So that's why in particular in windy conditions, that it's important to bundle up against the cold. And then to have your home ready, to have your chimneys checked, to make sure that your heating supply is ready to go. If you do have bags of salt for your driveways, to make sure that's all prepared, that your snow blower is ready to go, that your snow shovels and your ice scrapers are all nice and sharp as we get into the winter season. And then of course, to have an extra stock and an emergency kit in your car to be ready whenever you need it. And then all of our winter forecasts can be found on our winter page at www.weather.gov/btv/winter. So you can find the latest information on that as well. All right, so here is our next review question here. I'll open up the poll for this one. When is freezing rain most likely here in Vermont and northern New York? That should be open on your screen now. All right, all the votes are in. Here are the results for that. So the month of December is when we typically see freezing rain here in the North Country. December is our most favorable month for freezing rain in our area. So December is the correct answer there. All right, go back to, excellent. All right. So at this stage, are there any questions before we hop into the next segment of our presentation, which covers winter storm tracks and why winter tends to have these more dynamic storms? Seeing nothing at the moment, but of course you're welcome to put in questions anytime into the chat, and I will, or into the question area, and I'll make sure to get those answered as I can. All right, so let's move on to winter seasons and the role of the jet stream in winter. So a lot of what drives the dynamic patterns of winter is the thermal contrast between us and the tropics. So in the middle of summer, there's not as much of a contrast. We might be 85, 90 degrees here in Vermont, but Florida might be 90 or 95. The contrast between us and the southern latitudes isn't really all that great in the summer. As we get into winter, that starts to change. It becomes more like, say, 0 degrees Fahrenheit here, where it still might be in the 60s across Florida. And so that greater contrast between temperature, the atmosphere is going to want to try and preserve some kind of balance in the atmosphere. And so to do that, that typically results in faster winds to try and drive these thermal contrasts and restore some of that balance. So as a result, the jet stream is stronger in the winter months compared to the summer months. And because of that, we tend to see more dynamic features, and that's when we start to get nor'easters developing. These stronger areas of low pressure typically develop in the wintertime due to the influence of a stronger jet stream. And then, of course, one of the big influences to our seasons is the temperatures out in the, even just the equatorial Pacific have an impact on things like the jet stream. So there's the El Nino, the case where sea surface temperatures in the equatorial Pacific are above normal, and then La Nina, where the sea surface temperatures in that little area of the equatorial Pacific are below normal. And the discovery of this pattern actually originated from fishermen off the coast of Argentina, noticing that their catches were affected by these water temperatures in that area. And so the original method was focused around these waters off of Argentina for these fishing industries. But since then, it's moved to more broadly look at this larger area of the equatorial Pacific since then. And so we are forecast to have a La Nina pattern again this year with below normal temperatures in the equatorial Pacific. And again, the big impact that this has for our winter forecasts is that it tends to have a more variable polar jet stream. So for areas like Arkansas, typically the conditions are a little bit wetter and warmer for most winters. Here in the North Country, it actually is a little hard to determine what exactly those impacts are for us because the jet stream tends to be variable. And in our area, it all depends on where this exit region of these jet streams are. If it happens to be to our south, we tend to be fairly cold. But if it moves to our north, then we end up being fairly warm. And this also impacts the moisture that we can get either from the Gulf of Mexico or from the Great Lakes. So due to this variable jet, we tend to not have too big of an impact to, or it's hard to say which direction we lean, either warm or cold, or wet and snowy, or dry, but it tends to mean we don't have just one prevailing weather pattern throughout the winter season. Climatologically speaking, this is how much snow we have had climatologically from 1991 through 2020. We have typically anywhere between about 50 to 100 inches of snow across areas like the St. Lawrence Valley, the Champlain Valley, and the lower Connecticut Valley. As we get into the Adirondack mountain range, values start to increase as well into the Northeast Kingdom of Vermont, and as well as the spine of the Greens, where you start to get 100 inches plus, and as you get towards summit levels, you can get as much as 200 inches across some of our high terrain features. And as we get to the heart of winter, our coldest normals, typically in the mid to upper 20s for daily highs. So on average in our coldest part of the year, we don't get above freezing. And for our low temperatures, Saranac Lake, always a very cold spot. Usually near zero is its average in the winter. But for most of the broader valleys, it can range anywhere between the mid single digits into the lower tens for our area. And so what does our snow day number look like? How often do we see snow on a day-to-day basis? Typically in the heart of winter, looking at this period of December, January, or February, you'll see that each of these months we have snow about 9 to 15 days, or about 25 to half of the month. There is at least a tenth of an inch of snow occurring each day. On more of our active days, it can be as much as 22 days out of the whole month. How much do we have the big events where we see more than 6 inches of snow across our area? It might actually surprise you that we don't see these big events all the time here. We tend to have anywhere between 2 or 3 days of the winter season, covering, of course, December, January, and February, where we see these snowfall amounts of greater than 6 inches. So we are just enough inland that we're not always affected by the coastal nor'easters that can sometimes drop a foot of snow. Our average of getting about a foot of snow is generally once every other year. We've continued the streak over the last several years, though I think we've had at least a foot of snow at some point in one day across the last 4 years in a row. So it's actually not a common occurrence to get a foot of snow at least one day out of the year. So the big events don't always come too often. In more of our active years, typically about 5 to 8 days for each of these different locations across our region. And then this is the latest information out of the Climate Prediction Center as far as the seasonal outlook. And as a caution with all of these, to remember that it's looking over a period of 3 whole months. And as a result, it's not going to capture these 1 weeks of very cold temperatures or 1 week of very warm temperatures. It's going to average and smooth out a lot of those features. It's a very broad brush that's painted across the area. But in general, it looks like parts of southern New England and coastal New England into southern Vermont, the pattern looks to lean above normal. And as far as precipitation is concerned, it looks like parts of northern Vermont and northern New York should be at least slightly above in terms of favoring what kind of precipitation pattern that we expect in the area. All right. So before we move on to the different kinds of precipitation types like freezing rain and sleet and the different kinds of winter storms we can experience, are there any questions about the climatology of snow or the seasonal forecast here for the North Country? Precipitation types and winter storm tracks. The number one consideration when it comes to what kind of precipitation that we're looking at often is this one question: where is the low tracking? Since the area of low pressure, there is a cyclonic wind field around these areas of low pressure. So where exactly they track determines what kind of air mass that we get. If the low tracks off to our north, we get south winds, and these south winds are going to bring in warm air from lower latitudes into our area. So a low track that's well to our north oftentimes is going to result in rain or some kind of mix across our area. It's not every day we get a pure snow event out of a low track that moves off to our north and up the St. Lawrence River Valley up into Quebec province. Now, things get a little more complicated when the area of low pressure tracks very close to Vermont and northern New York. If it tracks into our area, we have some cold air in place, but we also get at least some level of warm air that tries to move into our region. The forecast that we have for tomorrow has a little bit of a complicated situation where our forecast for tomorrow features a weak area of low pressure that's going to move into our area, but we also have a low that's to our south. In any of these cases, though, it all comes down to what exactly is the depth. What's the layer of warm air versus cold air in our area? If the cold air is very close to the ground and very shallow, or this southerly flow that's bringing in warm air up into our area is very strong, we tend to have a quick transition where we go very quickly from snow to sleet or freezing rain, and then finally to rain. However, if the cold air mass in place is a little stronger, deeper, where the warm advection, that warm flow into our area is not quite as strong, then we tend to get a little bit of snow and then a little bit of a wintry mix associated with that, but we don't always go to pure rain in these areas where the deep cold air is in place, preventing any more of a mix of precipitation. And of course, if the low tracks to our south, in this region, the 4070 benchmark for the latitude, longitude position of these low centers is well known across this area of the region. Places like Boston want it to be south of that location to get their snow. If it's north, then they tend to get rain. But for us, that track tends to be most favorable for us. So for us, if we want to see big wintertime snow events, then we like to see snow tracks that are just grazing the coastline. Tends to be most favorable for us to see these big snowy patterns without warm air intrusions that would cause a mix of precipitation. Now, if the low tracks too far to the south, say it moves off the mid-Atlantic coast across Virginia or North Carolina and doesn't really move north at all, we can miss out on that precipitation entirely, where it's just dry weather for us. All right, so let's talk about some of the complications to our weather forecasts, which come from different layers of freezing versus above freezing in the atmosphere. So of course, the weather is more than what happens here at the ground. The weather also includes everything that's happening up to usually the troposphere or the stratosphere, well above the ground, anywhere between 30,000 feet to 45,000 feet up in the atmosphere can have an impact on our weather. So when we talk about precipitation type, on the left-hand side of the screen is an image of what it looks like when we get rain. So at some point you have a cloud that sits below this area where it's minus 10 degrees Celsius. And so it starts out as a snowflake, and as it drops, it encounters this area where the temperatures are above freezing, and so it melts. Now, there sometimes are these cases where the air is a little bit below freezing sometimes as it tries to get back to the ground. But if the ground is still too warm, it won't make much of a difference. It'll make contact on the ground as rain. Now, if we have an area where the extending up into the atmosphere if it's entirely below freezing, or even sometimes if there is just right at the freezing mark, it's not usually quite enough to melt that snowflake entirely. So as long as the atmosphere is near to just below freezing, that dendrite of snow coming out of the cloud is able to fall as pure snow. Now things get complicated when there is below freezing air again near the ground. So in the case of freezing rain, the depth of that cold layer is very shallow. And sometimes it can be as small as 50 to 100 feet up that these layers can be below freezing. And so as a result, the snowflake melts as it reaches this warm layer. And then because the surface is below freezing, it freezes upon contact with the ground. Now, sleet is slightly different in that the depth of cold air is just a little bit greater than freezing rain. And so if that's the case, then the water droplet that falls from that initial snowflake into this below freezing air mass again, it has enough time to become an ice pellet before hitting the ground. So sleet is usually not quite as impactful as freezing rain is, simply because it's not sticking to the ground. It's more just kind of bouncing off of the surface. You can still get ice accumulation out of sleet, but in general, freezing rain is a little more dangerous due to the fact that it sticks to surfaces, to power lines and trees, and causes much more mayhem than your ice pellet or sleet. So again, the main difference between sleet and freezing rain is how much time the water droplet has to refreeze. If it doesn't have enough time, then it's going to freeze on contact with frozen ground. When we get into the early spring months towards March, especially areas of eastern Vermont or some of the colder hollows of the Adirondacks, dirt roads will be very slow to thaw, and so as a result, sometimes we'll get periods of rain over these areas where the ground temperature is still 30 degrees or so, often making for slick and hazardous roads just from the frozen grounds. And then one thing to mention is that the role of terrain is very important for our area. So cold air is very dense compared to warm air. So as a result, it tends to filter into our lower valleys, but it gets trapped between our mountain features. So as a result, the Adirondacks and the Green Mountains give this sheltered area of protection for these cold air masses that make them very prone to freezing rain. So unfortunately, our mountain ranges make us favorable for this freezing rain setup where we get cold air that's coming out of the north, where any warm air that's moving overhead, it's going to ascend over the mountains and completely miss this sheltered area of cold air near the ground. So unfortunately, that is the lot we're given with our terrain. The lower valleys will tend to be more prone just due to how dense cold air is compared to warm air. And this is a map showing the weather pattern from the infamous ice storm of 1998, where parts of the St. Lawrence River Valley saw ice accumulations of 3 to 4 inches as a result of this nearly stationary area of low pressure that was very slow to move out. And the terrain played an important part. Warm air was not able to lift above the Adirondack mountain range. And so as a result, you had this persistent area of precipitation, but areas like Messina never saw any kind of warming up. And so as a result, saw abundant freezing rain. So you might ask yourself, 3 to 4 inches of ice accumulation, did you see 3 to 4 inches of rain? That's not necessarily the case. Oftentimes, the process of ice accretion is more efficient than rainfall processes. So sometimes you can get more ice accumulation than you actually get precipitation. It all depends on the winds, how heavy it's raining also has an impact. It's a pretty complicated mess actually when it comes to freezing rain. We do not like dealing with it because it's quite a challenge both to forecast and to message, given that it's the accumulation of freezing rain is so specific to how shallow these air masses can be. All right, let's move back to the fluffier side of things. Let's move back to the realm of snow. So snow comes in all different shapes and sizes, and let's get a little bit of understanding on why that's the case. So when we're talking about water droplets in the atmosphere, when it gets below freezing, it actually takes a little bit before you get below freezing, usually, for water droplets to become these dendrites. So water needs some kind of feature, whether that be dust, dirt, or some other kind of aerosol to adhere and freeze. So without those kind of features, it takes even into the teens, or even sometimes when you get below 0 Fahrenheit, for water to actually become ice and then become things like our dendrites. So water can be super cooled, as we call it, where it's still water but below freezing. But up until you get to this prime area here, you'll sometimes hear us meteorologists refer to it as the snow growth layer, or the dendritic growth zone, where there's this favorable area, again, in the teens to just below 0, where you get these big fluffy flakes of snow. And this little line here is to show how much moisture content is available. So you get the most bang for your buck in terms of snowfall when you're in these kind of temperatures here. If you're too warm, then you don't get these ice crystal formations. Sometimes you'll get instead needles or columns, the bane of our existence up here for any of our snowfall forecasts, because they ride right against the line here. And then sometimes when your temperatures are kind of marginal, they tend to be very aerated. They'll have a lot of air pockets in them, or they tend to be very fine features. They don't tend to grow or develop like they do when they get to this favorable temperature regime. Get too cold though, and you get back to the opposite problem again, where these nice little hexagonal dendrites tend to not form as often when you get outside these temperature ranges. So when we talk about our snowfall forecasts, we are looking up in the atmosphere to see, do we have these points, do we have these temperatures around to make nice fluffy snow, or are we looking at needles that don't really adhere well, that doesn't really make for as good skiing weather as well. And needles in particular are more hazardous to roads and driving, as well as they don't pack in as easily as plates or our beloved snow dendrites. And needles often also have lower visibilities as well. So in general, we're most happy when we have our nice fluffy hexagonal snowflakes. So that was a little bit of a deep dive into looking at different kinds of snowflakes there. Are there any quick questions about that before we move a little bit further into into this part of the presentation? All right, I mainly wanted to get a nice sip of water from that. So let's carry on to look at what happens once our storms shift off to the east. Upslope snow is one of the big things that we face here that's a particular challenge, in that it tends to happen over a narrow region of our forecast area along the mountain ranges, and it can be very finicky to deal with as well. Once the low shifts east, if there's still a little bit of moist air sitting in the St. Lawrence Valley and a northwest wind, then our northwest facing slopes tend to have these almost continuous snow showers throughout the day. Sometimes it's not that big of a deal. You just get an additional trace to say 2 inches of snow. Sometimes we get scenarios where our summits can get feet of snow from these kind of scenarios, from these upslope snow events. And one of our coworkers is affectionately calls them bonus snow. So it's one of our trickier things to forecast as well. But we do have a few things that we can use to help us forecast these challenges. We look at what is the, we define the flow as being, say, blocked or unblocked. So what does this mean? Again, our terrain features here play a very important role to how our weather works around here. In the case where it's blocked, you have wind that's driving towards the mountain ranges, but whether by some kind of stable layer above the mountain ridges, or say the wind isn't just particularly fast, it's very slow and light, that wind can't overcome the mountain ranges, and so it's blocked. It stays in the valley regions, and the foothills into the Champlain Valley tends to get most of its snow in these areas of low pressure shifting east at this point in the event. However, if the flow is less stable, where we have maybe a semi-blocked case where you have the wind hitting the mountain ranges, but there's just enough flow where it's able to overcome those mountain ranges, then snow showers tend to not stick around quite as long, tending to be focused along the immediate foothills and along the mountain summit regions. So again, the two major factors, wind speed and how stable the atmosphere is. So the more stable, the slower the wind, the more snow we see in the valleys. The opposite of that, most of the snow tends to go downwind of the mountain ranges. So again, to visually show this, here's some snow accumulations from an unblocked pattern. Not much snow in the valleys, more snow just downwind of the mountain ranges. Kind of halfway between blocked and unblocked, you have most of your snow focused along the mountain summits where it might be evenly distributed downwind of the mountains and in the valleys. And then of course the blocked flow where you're not getting much downwind of the mountain ranges, but you'll have most of it in the lower valleys. All right. And of course, we can't discuss winter without discussing our major low tracks. The Alberta Clipper originates in the Alberta province of Canada. These usually, because they are driven from these continental air masses where they aren't really sinking down deep in the Gulf of Mexico or in the Atlantic Ocean, they tend to just have a narrow strip of very heavy snow as they track southeastward. So if we happen to be on the south side of, or on the north side of these lows as they track across, sometimes we can get quick heavy bursts of snow from an Alberta Clipper and then be clear by the end of the afternoon. Here's a radar depiction of a recent Alberta Clipper in January of 2020. Area-wide light to moderate snow across the area. And then, of course, the nor'easter, when we get low tracks that move up the U.S. East Coast. If we are just within the area of the northwest side of the low, we can sometimes get 1 to 2 feet of snow from these cases. Now, as a note, a nor'easter is not called a nor'easter because it impacts northeast, the northeastern U.S., but because of the dominant wind direction. So since it's offshore, the wind direction in a lot of these areas are out of the northeast, and they tend to be very strong. Since these are rapidly developing areas of low pressure in most cases, the wind speeds associated with them are strong, and that's why they tend to be most associated with blizzards in the area. So The storm of the century in March of 1993 certainly qualifies as a nor'easter, even if it tracked just inland, but large area of strong northeast winds and then heavy snowfall rates that occurred across the Appalachian Mountain Range and then into Vermont and northern New York, with a very pronounced radar signature with a large swath of moderate to heavy snowfall. And then, of course, snow squalls. Since we do have one person from Arkansas on the line, I don't think you've experienced snow squalls too often from the year, but they can happen, I believe, in that area of the world. But in general, they're most favored across parts of the Intermountain West towards the Colorado foothills, but they can also happen up here in the North Country. And how that happens, we get an area of relatively cool air, but we might have an Arctic air mass that's plunging towards our area. If Lake Ontario is still unfrozen, it usually picks up moisture off of Lake Ontario and then produces heavy snow showers in our region. I like to refer to snow squalls as a blizzard bundled into 30 minutes. They're very fast hitting. They have a rapid onset. So as a result, they can catch people off guard by the strong gusty winds greater than 35 miles per hour. And then the heavy snowfall rates that come with them also greatly reduce visibility. So I'd like to make a quick distinction here between snow squalls versus just heavy snow. Sometimes we'll see reports of snow squalls, but we look at the videos and there's no wind associated with them. So it's important to remember that snow squalls have both heavy snow, but also gusty winds. So when you see these two things together, you might have a snow squall on your hand. The whiteout visibilities and the rapid accumulations of snow can make these very dangerous to travelers, especially if you're on the roads and unaware of these changing weather conditions. It's easy to be caught off guard. So they don't, like snow squalls do not have the blockbuster snow accumulations of a foot or more. It might just be 2 inches, but it comes so fast that it tends to have large impacts into our area. Here's an example of one that happened in February 27th of this last year, where you can see the stark difference where it looks mostly clear behind the or in front of the snow squall, but incoming you can see a shield of very low visibility and heavy snowfall headed into the area. So one of the other dangers that can come from snow squalls is the flash freeze. With this, sometimes we'll have cases where we have temperatures that are just right around freezing in our area. You get this narrow area of snow that quickly causes some snow accumulations, and then you have very well below freezing temperatures that almost can instantly change the liquid on the road surfaces into ice. So a flash freeze is a particular danger as well with this. So sometimes impacts from snow squalls can linger behind the main event itself. And then of course, the blizzard conditions. So a blizzard is similar to a snow squall, but the one key difference between the two is that a blizzard lasts longer. A blizzard will last over a period of 3 hours or more, and you have to have sustained or frequent gusts to 35 miles per hour or greater, and considerable falling, or it doesn't even have to be falling snow. It can be blowing snow that reduces your visibilities below 1/4 of a mile. So in essence, you will barely be able to see say maybe 15, 20 feet ahead of you in these serious scenarios. It's been a while since we've had blizzard conditions here in Vermont and northern New York. The last time was in 2017, where we had blizzard conditions observed in Plattsburgh, I think in parts of Grand Isle, eastern Addison, eastern Rutland from the Pi Day storm on March 14th of 2017. That's been the last time when we had a blizzard up here. So in blizzard conditions, recommended to shelter in place in these scenarios. It's very easy to get lost and easy to get stranded with dangerous road conditions. Blizzards are nothing to sneeze at. And then of course, lake effect snow. We are just close enough to Lake Ontario and Lake Erie that we do get lake effect snow. At this point of the year, water takes a lot longer to change temperature than our air temperature. So at this point, the Great Lakes are still in the mid to upper 40s temperature-wise, whereas now we're regularly in the 20s here. So there's a lot of atmospheric instability. So with the right conditions, you can drive these heavy snow showers off of Lake Ontario or Lake Erie, of course. And this is from one of the blockbuster events in March 18th of 2014, where parts of this little area of Chickamauga, I'm terrible at pronouncing the name, I'm sorry, south of Buffalo, received over 65 inches of snow in less than 48 hours, whereas the town of Buffalo proper only managed 3 to 4 inches of snow. So big accumulations can happen if these bands of snow don't move off of the same spot from time to time. You might have these scenarios where you're nice and clear, but just down the road, you might see whiteout conditions from these lake effect snow bands. Under the right conditions, lake effect snow bands can extend over 200 miles away from Lake Ontario. So this was a case that we had on our leap day, where we had snow that traversed all the way into central Maine and into some, it looks like some of it got down east as well from this very favorable setup for lake effect snow that happened in late February. All right, so we're at our next review question. I'll open up the poll here. We have each of these options describe which letter here describes the difference between sleet and freezing rain. I didn't have enough characters in the poll, so it'll slightly differ from the presentation there. But which of these accurately describes the difference between sleet and freezing rain? Now it's been about 1 minute. We've closed the results of the poll here. The correct answer for the poll is the second choice, that sleet has refrozen before reaching the ground, where freezing rain makes contact with the ground first before freezing. Unfortunately, I didn't have enough characters to fully describe that, but in the case of A, freezing rain results in more accumulation of ice than sleet. And for sleet, you have more cold air near the ground than you do compared to freezing rain. So let me go back to sharing my screen here. So the idea that sleet has refrozen before contact with the ground is the correct option there. And then freezing rain becomes frozen upon contact with the ground. All right, so before we head into how we provide messaging and how we communicate winter hazards, are there any questions before we head on to this part of the presentation? All right, nothing seen here, so we will continue on. Let's look at the different products and the general timeline that you can expect from us when it comes to winter-related hazards. The first kind of thing is almost a little bit of a heads up. It's not a significant product in some regards. It's something that we issue when we're starting to see some signals for the potential of some kind of weather-related, winter-related hazard that we think that we might need watches and warnings for as we're going forward. So it can be something as far as 2 to 5 days in advance of us issuing headlines. So when we're starting to see potential is when we start issuing things like the hazardous weather outlook to start talking about and start the first level of communication of we're starting to see things but it's still a thing in the future when we start talking about our watches. Excuse me as I turn back on the lights here. As we start talking about our watches, that's when we start more actively alerting the public to the potential, still not guaranteed, of a warning level event. So we can issue things like blizzard watches, ice storm watches, wind chill watches, and winter storm watches. So we will try and issue things like watches when we expect the potential that we have a warning level event, sometimes 24 hours before the event. We prefer if we aim for 48 hours before any kind of winter weather event happens. So for snow events, we're actually doing an experimental test this year on different criteria to try and match more of an event-based approach. So we'll be looking now at more for 7 inches or more above normal for some of our warnings. When we get into the warning level events, that's when we start seeing the winter weather threat is very likely or expected to occur with widespread impacts possible. So with that, the time window for this is about 12 to 36 hours. And for snow, it's when we're looking at amounts of 7 inches or more for an event. For ice storms, that is when we start getting accumulations greater than a ½ inch. So up until that point, ice can be hazardous for road conditions, but it's not until you start getting accumulations like a ½ inch that you start getting more impacts to power and utilities. So once we get to this ½ inch threshold for which we issue ice storm warnings, that's when we start to expect more widespread power outages. And for wind chills, when you get these apparent temperatures that are 30 below, that's when you start getting frostbite in as little as 10 minutes when exposed to the elements. When we're talking about blizzards, again, looking for at least 3 hours where we have whiteout conditions, heavy or blowing snow, and frequent gusts to 35 miles per hour. So those are some of the winter hazards that we can issue. We start with the hazardous weather outlook. We go to the watch, and from the watch, we can transition to warnings or advisories. Sometimes if the weather pattern is changing rapidly, where there are a lot more things that could put a wrench in the forecast, sometimes the watch part of the process can get skipped, and sometimes we'll jump straight to warnings and straight to advisories. Advisories set below winter storm or warnings or blizzard warnings. We don't have a blizzard advisory. There's no kind of thing for that. But we can have ice storm advisories or wind chill advisories when we're dealing with cases that aren't quite at warning level potential. These cases are typically not life-threatening. They tend to be more of an inconvenience. Not to say that you don't prepare or plan for these kind of events accordingly, but as far as an advisory is concerned, the level of impact is typically minor, may be a little more localized and dependent on how well things are managed ahead of the event. So like a warning, an advisory is usually handled 12 to 36 hours from the onset of the event. And so for snow events, that's going to be cases where you have 4 inches in at least 12 hours or 6 inches in at least 24 hours. For ice storms, it can start as early as a glaze. It doesn't take very much ice to make slippery roads. So if we see any kind of ice in the forecast where we expect accumulations, we'll issue some kind of advisory. One thing to note is if there is both ice and snow in the forecast, we will just issue a winter weather advisory. An ice storm advisory is only ice. There's no snow expected in those kind of cases. So in the presence of both, just a winter weather or winter storm warning in those instances. And for wind chills, when you have conditions that favor frostbite in a 10 to 30 minute time frame, when apparent temperatures are usually about 20 to 30 below. So all the warnings are out. We've issued our products and issued our headlines. Like for today, we have our winter weather advisory out. So from this perspective, we've done everything that we do when we start communicating and putting out our messaging. At this point, we start going into collection mode, where we start digesting and looking at snowfall reports, whether or not we need to make any tweaks to our message or any tweaks to our forecast. At this point, we're all in data collection mode. So our weather observations, our stations, our spotters, co-op volunteers, cocoa rods, things like that. We're taking phone calls, we're receiving reports on email and social media, and we're collecting them and putting them into these local storm reports or these public information statements to process them through geographic information systems so that we can develop maps like the map there on the right. With that, that's how we verify how well we're doing. Did we get the forecast measurements that we expect? Are we overachieving or underachieving? Do we need to adjust our forecast and how we're talking about the storm from this? And so from that, we'll get a sense of how well did we do? Or do we need to change? Or do we need to take a deeper dive into what happened for the event? So the reports that you provide come in at this point in the process and helps give us a complete picture of things that are happening. Like say you can see on this map, we typically don't have a whole lot of spotters out in the St. Lawrence Valley. So sometimes we are left with a little bit of a blank of what exactly happens. We have, again, radar satellite estimates, but a spotter can go a long way into help filling in some of the gaps in data, especially when we're dealing with cases like on this particular day. This is an early season snow event, very elevation dependent, where you got rain snow kind of mix where you don't get as much accumulation in the valleys, but near summits you can get nearly a foot. So your reports go a long way into helping us get a complete picture of what we're looking at weather-wise. So with that, how do we measure snow? This is the official method for how we measure snow. Here are some of our recommendations. So why do we use a snowboard? There are two key factors as to why we use a snowboard. One, there is heat radiating off of the earth, and so as a result it can melt snow from below, and as a result not give you an accurate measurement. The other problem with not using a board is that you have snow collecting on top of your blades of grass, and so if you just stick a ruler in your lawn, what ends up happening is you measure just a little pocket of air, not giving you the most accurate measurement. So what we recommend and what is the official method is to measure the total depth of that snowboard every 6 hours and then add that number up as you go through the event. Every 6 hours, wipe the slate clean and start the process over again. Sometimes if the hourly rates are very heavy, or if you're dealing with scenarios where it's 34 degrees outside and snow is melting before a 6 hour period, sometimes it's okay to adjust some of what you're doing as far as measuring snow is. It's not a precise science, especially if you have a lot of wind. It can drive snow off of the board or on the board. And so as a result, it can be hard on windy days to get an accurate snow measurement. It's not a precise science by any means. It's very challenging to accurately measure snow. So this is the way that we best quality control our snow measurements. And we recommend, just in case, to take an average of measurements on the board. So take like 4 or 5 spots on the board and see what you get, and add the numbers together with an average of what you see. So that can sometimes take out some of the guesswork for blowing snow, or when you're dealing with like some parts of the snowboard may have more snow than others, or an uneven surface kind of deal as well. So this is our best way to measure snow. Where you measure snow is just as important. It's important to have an open area away from trees or buildings, so that you don't have around trees. The trees will catch some of the snow and not make it to the board, or you can get the ring of no snow around the tree sometimes. Or against a building, snow can pile up against the side of a building and not give you an accurate measurement. So ideally, you want an open spot away from trees or buildings to get you the most accurate snow measurement. So if you are concerned about not having the best spot, again, like I mentioned, getting an accurate snow measurement is really tough, all things considered. Most people send us in actuality a snow depth measurement, but we make do with what we can, and we quality check to make sure that nothing is too outlandishly far from what is expected. So that's a general guideline, but if all you have the capability of doing is looking at what is on your front porch, we understand sometimes that that's the best that can be done. And then, of course, hopefully we don't have to do this very often. How do we accurately measure ice? It's easiest to do it on a flat surface. And fortunately, the flat surface is the official method as well. If you have a flat surface, just take your ruler and measure the thickness of the ice on that to get your ice accretion measurement and report that to us. If you do use a tree branch, just make sure that you remove the tree branch from that measurement. So you'll take two different measurements on either side of the tree branch and then add those together at the end. Additionally, though, the ice tends to collect on these kind of cylindrical surfaces like power lines and tree branches a little differently than a flat surface. So with that, there's also a conversion factor. So if you are measuring from a tree branch, send us a photo of that and we'll be happy to do the conversion factor for you. If you do happen to be taking, say, a radial or tree branch measurement, let us know that that's the case so that we can make the proper conversion for that. I've alluded to the idea of a weather app. Oftentimes we receive reports from the phone, email, or social media, but if you have a smart device, you can also submit reports with the tap of a finger using the MPing app. This is from the NSSL is the short of it, and they're a research group, the National Severe Storms Laboratory, and they are collecting these reports and using it for some research as well. You can download the free app and use your location services to tell us the precipitation, what's it like, is it changing, right where you're at. And so this is one way you can support research as a citizen scientist. And you can report off as often as you'd like. Sometimes I have loaded up the reports and I can see someone just driving down the interstate reporting as they do so. Of course, if you have your passengers do that, don't do that while you're on the road yourself. Be safe when you're doing it, of course, but you can do it wherever you're at using your location services. And below, I have how you use it for freezing rain by hitting select report type. And then this opens up the menu and you have all kinds of different ways that you can report, like either rain or snow, hail, wind damage, tornado, a lot of the things a spotter might be interested in. And we'll select freezing rain, rain/snow. And that opens up the next menu where you have all kinds of different precipitation types. And then you can select freezing rain. And then from there, it'll take you back to the map that you're at. And then you can submit your report from there. So it can all be done in just a matter of seconds to report whether you are observing in your area. And so with precipitation types especially, it's very handy. It helps us see transition regions where you're going from snow to rain to sleet and freezing rain. This is something that we can map and see these transition regions in real time, which can be something that can be a challenge to do. There's also new to MPing is the ability to report with snow squalls. So again, you go to that select report type. This one's under a slightly different thing. It's under reduced visibility. under that tab, but you can select snow squall under that. And this is being used to help us verify this snow squall phenomena, which we only started issuing warnings for back in 2018. So it's still a relatively new thing that we're pursuing. And you can, again, help as a citizen scientist and as a spotter by submitting snow squall reports. So with that, that's the imping method of reporting these observations to us. We've talked a lot about different weather phenomena, load tracks, and everything from freezing rain to sleet to nor'easters and Alberta clippers. And what do we do with all of this information? Well, the best way to for us to receive your phone calls and receive your reports is via a phone call. We have a toll-free spotter line that's listed there. But then we also have social media. We have pages on Facebook and Twitter. And during events, we have someone regularly monitoring what conditions are like and looking out for your reports. We also have amateur radio. We have two. One is bouncing off the Moncton repeater, and another is bouncing off the Whiteface repeater. And we are listening into those stations during events for those reports that are being relayed over amateur radio. We also have on our webpage www.weather.gov/VTV/storm report. That has a page where you submit a lot of the information we talked about, the name, the time, what exactly is happening. All of that information we talked about is what a spotter reports is all in that form, and that gets emailed to us in operations, and so we can see your reports that way as well. There's the imping app, which I've mentioned here, and then of course we often encourage sharing of photos, especially when we're dealing with tornadoes and funnel clouds and things like that. A photo goes a long way, or especially a video in a funnel cloud case to see rotation. But photos are a helpful way for us to help confirm and verify what you're seeing, and it helps us. We have multiple expert eyes that can then take a look, and we can come to a consensus of what's being observed. And photos are really good with ice measurements as well. So that goes into the different processes for what kind of winter headlines we issue, how we communicate them, and how we use reports from spotters and how we collect reports from spotters. So here I have the last review question here for our presentation this morning. So which timeline listed here is the possible flow of headlines that can come from the National Weather Service for these specific weather hazards? So launch the poll here. So take a quick look what these hazards are. There are two correct answers in this setup. All right. So with that, we've now had about a minute to look over the question here. So for which timeline is the possible timeline? The correct answers are D and E. So let's take a look at that. Let's go back to our screen. All right, so let's look at each of our different options here. Now, A, when we're talking about going from advisory to watch to warning, the watch is always going to come first. We won't transition from an advisory back to a watch. If we do change the forecast, like increase our snow or ice totals, we will take the advisory and upgrade them straight to a warning. The watch will always come before any of these advisories or warnings. The hazardous weather outlook, yes, it's first, but the watch always comes before a warning or advisory. So B can't be correct. And then C, once we do issue the warning, we will, as time goes on, say not the entire area is in a warning. Sometimes we will go back and do the hazardous weather outlook again sometimes, but it never goes back to being that watch part of the forecast. The watch is always going to come before a warning or an advisory, except in the case where we feel like the time range doesn't quite match up to it. The change of weather conditions requires us to, right at that moment, jump straight to a warning. Sometimes that is necessary on our part. So that is why E is one of the correct choices. And then the other correct option is D, from the hazardous weather outlook to the watch to an advisory. Slightly a bit of a trick question, in that a watch is not always going to translate to a warning. Sometimes it will translate to an advisory. We issue watches when we see the potential for a warning criteria, but if we look at new data, looking at what's happening, say, upstream across Ohio, and we see they are underperforming, we might choose to take the watch and simply say we're going to be going with a winter weather advisory in some of those cases. All right, so with that, we're starting to get towards the end of our time here and the end of our presentation. Are there any lingering questions on your minds? Right, I'm not seeing anything in the question tab. So we'll go ahead and wrap up the presentation here. So just as a quick summary of what we've discussed today, a reliable Skywarn spotter is going to provide important ground truth information, that's sometimes even life-saving information about down trees or lines, funnel clouds, and heavy rain, wind damage, things our radar and fancy tools might not necessarily see. Ground truth information can't be beaten, and a trained spotter is a very valuable public service that someone can provide. We talked a lot about our different winter hazards, from ice jam, flooding, to wind chill, to heavy snowfall and the hazards it provides to our driving. We looked at our different kinds of winter storms. We looked at our climatology and our seasonal forecasts with relation to snow, ice, and temperatures. We didn't talk as much about strong winds, but strong winds are a possibility at this time of year that can cause down trees and power lines in our area. And then we talked about the timeline of how we communicate our forecast information and the role that a spotter plays once we go into data collection mode. Again, whenever we're talking about any of this stuff, your safety should come first. And as any of our spotters or any member of our public, we never want anyone to put themselves in harm's way. To provide information to us, hopefully ahead of the event coming on Wednesday, you have your vehicles winterized and ready to go, and you have your emergency kits, spare car batteries and things like that, ready just in case the worst happens. It's important to consider your safety as we head into the winter season. Even though we might be a little more trained here in the Northeast against driving in snow, still the number of accidents do typically increase at this point of the year as people deal with these winter weather hazards. So with that, a reminder of important things for a spotter to report can include tornadoes, water spouts, or funnel clouds, any dangerous or severe thunderstorms, like if you're observing hail, lightning damage as well, heavy rain. If there's ice jams that you observe on rivers, we'd love to hear about ice jams because they have such an important role to play as we go into the spring snow melt. Heavy snow, especially if things aren't going according to forecast, like things are starting to pile up a little faster than expected, or when we're dealing with transitioning precipitation types, we like to know that. And of course, what your ice accumulations look like as well, all valuable information that a spotter can provide. So thanks so much for attending our session here this morning, and thanks Jacob for attending all the way from Arkansas. Sorry if there was any confusion about that and some of that in the region, and hopefully some of this information was useful to you as well. If you are interested in becoming a part of our spotter network, if you live here in Vermont and Northern New York, feel free to email me. I have my email up there, or call us at our office at any time to inform us that, hey, yes, you've attended the course here this morning, and we'll be happy to follow up with you to incorporate you as a part of our spotter network. Some of the ways that you can contact us and report to us again are here at the bottom of the screen. And if you would like a copy of the presentation, feel free to reach out to me, and I'd be happy to send you a PDF-friendly version of it that doesn't have all the animation separated out. So thanks so much for listening. I'll stay on for at least another minute here to answer any of your lingering questions, but thanks so much for joining us here this afternoon, and hope this was a good use of your time.